Hi guys, we're going to go over quickly a topic today called simple harmonic motion. This is basically going to be a bridge topic into waves, which we're going to spend a long time on. So I'm only consider an introduction to some general topics here. Although in this slideshow I'm going to discuss some formulas at times, just the idea of it is what we want right now. You're not going to have any problems on this stuff. So if I'm going quickly, just take it all in and we'll break a lot of this down more in the future as we lead into waves with this idea. But the topic is simple harmonic motion, often abbreviated SHM. And objects in simple harmonic motion are in some form of periodic motion. Periodic motion means back and forth or vibrating or something like that, which is actually what all waves do. And that's why this topic is a topic that often leads us into waves. All right, so SHM, again, simple harmonic motion. We could think of it as back and forth vibrational motion. We usually use pendulums to study SHM. And there's two general types of pendulums, which I'm going to flip to real quick here. One would be the spring pendulum. That would be taking a spring and a mass and making it bounce up and down. Play with that. So that object is in simple harmonic motion. Now, a little detail about simple harmonic motion. Don't get too caught up in this, because we're not getting real in depth in this. But to technically be in simple harmonic motion, the force making the object go back and forth is supposed to be mathematically directly, very directly, excuse me, with the displacement of the object. I'm just throwing that out there. Don't worry about too much about that statement. Another type of pendulum is just our typical pendulum, a swinging pendulum, like we use to study energy topics, like a mass on a string or something like that. Another detail not to worry about, but I kind of have to say it, is that one little feature with swinging pendulums is that they're actually only in simple harmonic motions at small amplitudes. Notice when I raise it higher to one side on the top, you see the angle grow. That angle is the displacement angle. And it turns out technically an object at higher amplitude swinging back and forth like this on a simple pendulum, we call this, is actually not in SHM. It's still in periodic motion, but there's a group of formulas you're allowed to use with SHM. And the reason comes from a kind of a complicated mathematical reason. So the point is, when we study pendulums in SHM, string pendulums, we only study them in small amplitudes. What that means is usually between 0 to 15 degrees. So right now I set this at about 12 degrees. But again, don't worry about the fine details with that. It's just that when you see things studied like this, systems like this in SHM, it's always going to be at small amplitudes. But those are the two kind of systems we often study. Sometimes spring pendulums also go side to side, like on a horizontal surface. But either way, those are the two most common systems to look at with this certain type of periodic motion we call SHM. Okay, back to the notes. Just some certain terminology that we want you to start getting familiar with, because we're going to use many of these terms with waves. The amplitude, all right? What amplitude of an object in SHM is this max displacement from the rest position. So I'm going to pause this right now. So this dotted line on this pendulum represents the equilibrium position, where, you know, if you let it go, eventually, due to outside forces, it's going to come to a stop, right? And that's where it would stop it going straight down. This position, or the similar position on the opposite side, is known as the amplitude, max displacement away from that. If we go to the spring pendulum, And we pause it, and right at the very bottom or right at the very top of its spring. Hard to pause there. So right at the very bottom or very top of its swing would be the amplitude of a spring pendulum. And amplitude, you probably already heard of that term, often is common with like sound waves, but actually is common with all waves, as we'll learn in the future. And moving along, one of many reasons that objects in SHM are just like any and all waves, because if we actually graph their motion or their velocity or their acceleration over time, of like, let's say, a spring pendulum in this picture, bobbing up and down, back and forth, it actually makes what we call sine waves, or cosine looking waves, for all you that remember that from trig. But that's like a typical wave pattern, right? Up and down, up and down. So any of those three core features that we've learned about all year, position, velocity, acceleration, time graphs, they're all periodic and they go back and forth as such. We could see that in this simulation as well in real time. So I'm going to start a string pendulum. And if we graphed its displacement over time, you can see a little dot going on this. It makes a graph that looks like a wave, but we call this a sine graph mathematically, a sinusoidal wave pattern to be specific. So that's where these objects in motion and waves really have a lot of similar characteristics and graphical features especially. Moving along, I'm not going to say much about the potential energy in spring pendulums, although it can be discussed. We learned in the past there's potential energy due to gravity by lifting objects up. Well, springs can store potential energy known as elastic potential energy. Other than that, don't worry too much about it. Also specific to spring pendulums is something called Hooke's law. This is just a quick way to find the force on a spring. Force equals negative kx. X is the distance stretched and compressed. K is something known as the spring constant of the spring. It's kind of like a value that determines how like strong the spring is, like stretchy wise, basically. But again, we're not going to do anything with formulas in this section until we to waves themselves. I already looked at string pendulums as examples, and we're going to discuss a phenomenon known as mechanical resonance. And you guys are going to watch an Edpuzzle video on a very popular disaster that happened many years ago due to this phenomenon. But as the definition states here, the amplitude of any vibrating object be greatly increased by applying small forces at regular intervals of time. One of the two examples I have here is pushing a child on a swing. Now, a child on a swing is really similar to just a simple pendulum, something like this, right? And in particular, pushing a child on a spring, so not a spring, I'm sorry, swing. If you stand behind them, you don't necessarily have to push harder and harder to make them go higher and higher. As long as you push every time they come back to you, to a point, they will get higher and higher because you're pushing at regular intervals every time they swing back towards you at this position. And it only can increase so much, but it can increase little by little till that amplitude of that swing gets higher and higher. Now, a child or anybody on a swing that is swinging without being pushed is also undergoing mechanical resonance. We should all know that if you're on a swing and you just start rocking your body and legs sporadically, you don't start swinging, you just shake a lot, right? But if you bring your legs back and move them forward in a kind of harmonic, regular interval pattern, you will start making yourself swing. You're actually making mechanical resonance occur on you. So like every object has what's called a natural frequency of resonance. And if you get a force to place regular intervals, placed at regular intervals that matches that resonant frequency, we call it, the system will start to shake a little bit, then a little more, then a little bit more, up to a point. If you've ever seen somebody, or probably not seen it live, but maybe on TV or something, you've seen clips of somebody breaking glass with their voice, like a crystal glass or something like that. What's happening is their voice is vocal cords is providing sound waves that provide the forces at just the regular intervals, which we really call the frequency, to make that glass shake. And it shakes so much and increases the amplitude of shaking to the point where the glass, since it's a solid, can't handle it anymore and breaks. There was a similar thing that happened to a suspension bridge in the 1940s, and that's the video you're going to watch about. I'm also going to try to post a YouTube clip of maybe sound breaking glass as an example of this as well, so you can take a look at that. All right, and the last final thing, just known as damping. Both of these simulations I was just playing, I turned off damping, or in other words, damping is kind of a catch-all term, excuse me, for like resistive forces like friction and air resistance that cause it to stop. Notice this pendulum just keeps going and going and going between its amplitudes, and doesn't look like it's ever going to stop. But if I set, let's see if I can do it on this one. I'm not sure if I can. Let's go to the other one. Here we go. So this one's just listed as friction. I have it set as none. But if I do turn any on, that's known as damping. And if it's damped little by little, it'll eventually not reach the max amplitudes it was originally set at. And we're not going to wait forever here, but you can see it start to not hit those blue amplitudes anymore it started at, those blue markings. And eventually it will settle down to its equilibrium position. So again, we just call that idea damping, but it's just due to the outside forces of friction, air resistance, anything resistive that's trying to stop it. All right, I know that was quick, but that's pretty much your intro on simple harmonic motion. And again, we're not going to do a whole lot with this past today's assignments. So it's going to lead us later in the week